At PerkinElmer, we're committed to providing our customers with leading solutions to the meat and poultry industry. And we're pleased to introduce Charlie Kauffman, our Senior Product Specialist, who will discuss applications for our RVA instrument.
Hey, thanks. Yeah, like Paul said here, we're going to be talking about some of the performance analysis metrics that we use for meat stabilizer components, and then for some of the dry blends that go into batter and breading systems. And we'll talk a little bit about why that's important in terms of an overall quality perspective to measure functionality in this way. So the device that we're going to be talking about throughout here is called a Rapid Visco Analyzer, or we call it an RVA. And basically what the RVA is it's a little robot chef, and it heats and cools and mixes the sample according to whatever program you send to its little robot brain. It's the industry standard tool for starch quality characterization. Obviously, it does a lot of work in flour quality and flour systems, but also in hydrocolloids and stabilizing ingredients, and ingredients that are designed to bind up and retain water and liquid fat and impart texture, things like that. And that's really what we're going to be talking about today. It's also really highly descriptive for multi-component dry mixes. It's a great way to play mix detective. If one component is out of balance with respect to control, you will detect that deviation with performance, even in instances where you can't necessarily detect it with compositional or approximate analysis. And then it also allows the user to visualize and quantify the effects on ingredient performance of processing conditions that have led to those ingredients being the way they are, right? So things like spray drying, shear treatments, pH, all that stuff. If it has become abnormal in any way, this little robot chef will tell you all about it. So stabilizer blends, whether we're talking about dairy applications or meat applications, they're there to bind up water, lend some texture during cooking and gelation after cooking. And they're not really there to lend any sort of nutritional benefit or anything like that. They're not there to impart flavor. They're all function. And that's really our bread and butter here with this device. So stabilizer systems will have a starchy component. Sometimes it's a modified starch. Sometimes it's something like rice flour. Often they will have a gum or a hydrocolloid like gelatin or carrageenan or a xanthan gum or something like that. Sometimes they will contain a protein powder, but whatever they are, it's usually a multi-component dry blend that you hope contains everything in a proper ratio, and you hope that the individual components are behaving the way that they're supposed to behave. So we'll talk a little bit about starch here. It's a good place to start. Starch is a really, really common component of stabilizer systems, whether in the meat or dairy industry, whether it is a pure or a native or a modified starch, or whether it's as part of a flour ingredient. Starch is really one of the functional drivers of a stabilizer system. So with starch, the functionality comes from its performance during cooking. So you'll hear starch chemists refer to starch gelatinization and starch pasting, and both of those are related to starch cooking behavior. Gelatinization doesn't really result in a viscosity impact of that starch solution, because gelatinization just refers to the melting of the internal crystalline structure of each starch granule. Here you can see a microscopic image of starch granules that have been stained with iodine, and these have not been gelatinized. They're still raw. They're still in their native state. You can see there's like a little X or a little Maltese cross on each one of those granules. And that is a refractory effect, and that is due to the internal, not disrupted crystalline structure of the granule. So if you continue to add heat to this system, those little crosses will melt away, and that is because of the literal melting of the crystalline structure of the granule. There's no viscosity change associated with this, but it is immediately followed by granule swelling and granule rupture, the process that we traditionally associate with the term starch pasting. And of course, there is viscosity change associated with that, and that's really what's important to measure. So obviously in the food industry, we know that all starch is not created equal. Some of them have been highly modified for specific functional purposes, and even some native starches perform better than others for different applications. So they lend, each of them lends their own set of concerns and drawbacks. Tapioca starch, for example, takes in a lot of water and builds a lot of viscosity during pasting, but then it does not retain that water very well during gelation. And so that can introduce a lot of free water into a system where the proteins have already been cooked and degraded, and can cause some problems that way. And then potato starch is temptingly cheap ingredient, and it's a natural ingredient. But potato starch granules are physically the largest starch granules, and they're really easy to damage mechanically that way. So there's some additional performance consideration because potato starch is easy to damage. We all know that there are myriad ways that you can modify starch. You can cross-link it, you can acid thin it, you can oxidate it, you can degrade it with enzymes, you name it. And the idea there is to reduce the average molecular weight range of the starch molecules into a target zone. And the reason that the RVA is the industry standard tool for starch modification characterization is that in this context, viscosity is a function of molecular weight. So as you change the molecular weight range of the starch ingredient, you're changing the viscosity correspondingly. And so you can babysit that process by measuring viscosity. And we'll talk a little bit in a minute here about the inherent waxiness of the starch and its effect on overall starch viscosity. But it has to do, again, with the fact that starch is a function of molecular weight, and waxier starches have a higher molecular weight. So some of the factors that impact starch performance here, starch can be damaged by heat, starch can be damaged by sprouting of the grain that it came from, chemicals, enzymes, inherent waxiness, shear damage, and in the case of starch that has come from drought corn, for example, there will just be less of it per kernel. So that's more of a scarcity issue than a performance. Let's talk a little bit more about waxiness and the relationship of molecular weight to viscosity. So starch has two molecular components. There's amylose and amylopectin. And amylose is a real small straight chain Lincoln log of a molecule. It stacks really well with itself, it hydrogen bonds really well with itself, and it forms a chemical film in doing that. And so it lends a lot of shine, it lends a lot of crispness, like brittle texture, and it is a relatively small molecular weight, and so it does not impart a lot of viscosity. Amylopectin, on the other hand, is a big, like, tumbleweed of a molecule. It has a huge molecular weight, And because of its shape, it doesn't really stack very well with itself. And you can think of this viscosity relationship in a way that if you had, let's say, a pickup truck where the bed was full of like little Lincoln logs, you could jump up and down. You could jump up and down on the top of that pile of Lincoln logs, and you would not feel much give, right? And that's really what we're talking about when these things stack very well with each other and they form a film, right? It's a very hard surface. But if you raised the bed of the pickup and went to dump it all out, they would flow out pretty easily. They're pretty small. They can slide around pretty easily. By the same token, if you had the bed of the pickup full of tumbleweeds, you could jump up and down on top of them. It would be very springy. And because they don't stack very well with each other, they confer a lot of expansion. But if you went to dump them out of the pickup, they would all come out in one big flow-resistant glob. So that's a good way to think about the relationship of viscosity. Like here we can actually see an RVA result that shows 2.5 grams of waxy starch versus 3 grams of a normal native starch. And that really illustrates the disproportionate impact that waxiness has on viscosity here. So we talked about starch modification characterization, but the only thing I really have left to harp on here is that if you're going to monitor modification processes, whether you're making tortilla flour or a modified starch, or whether you're buying a starch where you expect consistent performance, it really pays to measure that starch performance and that degree of modification with a viscosity, a pasting viscosity based measurement like this. So regardless of the way in which that starch was modified, you can track the impact of that modification with the RVA. So another component of stabilizers in meat is the gum and hydrocolloid family, and so this can include things like gum, pectin, gelatin, carrageenan, things like that. And these are really there to take in water at low temperatures and bind up water without releasing it back into the finished food. So they impart a lot of texture in doing this. So there's some palatability considerations with introducing too high of a level of hydrocolloids. You can see here that the viscosity performance of these ingredients is important to monitor too, and they're really affected by the osmolarity, say, of the system that they're in. So we can monitor discrepant performance in a really salty environment or in an environment where pH has been modified. And all of this is a little complicated to look at, but all of this is to say that if there is something about the system that has caused a functional variation in that ingredient, that's caused it to perform differently, you will find it with this analysis. We don't see this very often in meat stabilizer systems, but once in a while you will see the introduction of a protein powder, whether it's dairy protein or whey protein or even meat-based protein. And I just wanted to spend a quick second here talking about the built-in variability that exists with these ingredients. They can vary based on the season in which they were harvested. They can vary based on the filtration technique, the purification technique that was used. any buffering agents that we use to extract those ingredients, and then the physical way in which they were processed can cause variability in the way that they hydrate and perform. So now, having said all that, we can get kind of to the fun part. So batters and breadings, really, it's well-worn territory for the food industry, right? It's a multi-component dry mix. It's really not that different from baked mix, right? Like for cakes or bread or something like that. But it's designed to perform in a frying environment or in a conveyor oven environment. And there are some added considerations because of the way that this type of food is intended to cook that make it really important to keep close tabs on ingredient performance and the performance and the overall quality of the dry blend. So when you optimize the batter breading ingredient blend, what does that mean? Well, that means that you are making sure that the ingredients that come in to the plant before they become a breading mix, say, making sure that all of those ingredients are normal, are behaving the way that they're supposed to behave. This device gives you a really easy to interpret way to compare performance of something that's coming in right now to a historical control, something that you know works well, was optimal. So once you've vouched for the individual ingredients that come in, you can evaluate the multi-component dry blend and make sure that everything that's in there is supposed to be in there and that it's all in there in the correct ratio. So the effects that all this have, obviously it optimizes crispness. If you're optimizing starch functionality and flour functionality, that's really the driver for crispness product. And it also optimizes the development of color in the fryer or in the oven. So the way that these ingredients brown, the final color that they attain, all that stuff is related to not just the seasoning, but the starch and the flour components that are in those mixes. And perhaps most importantly, optimizing the ingredients and optimizing the mix also minimizes the problems that these ingredients can encounter during frying, especially problems like flaking and blow off during the fryer that can create a surface of exposed meat that should be covered by a batter or a breading. Dry mixing is hard. Things go wrong during dry mixing. Things that are supposed to get added by hand get left out, they get forgotten, they get added twice sometimes. Sometimes a vacuum conveyor will get conveyed or will get clogged and something will get added incompletely. And sometimes they don't leave the ribbon mixer on for long enough and you don't have a homogeneous dry mix. So you've got big pockets of flour or seasoning or starch or some striations in the totes of breading mix. So you don't want any of this, but not all of this is things that you or things that you can pick up with like an NIR device or a pH meter or anything like that that detects proximate or compositional changes, because they aren't often big enough or visible enough to those devices for you to see them. And the way to reliably detect them and identify problems is through performance-based analysis with devices like that. So again, we're ensuring that everything that comes into the mixer is on its own normal. optimal. In food quality control, normal and optimal generally mean about the same thing. And then if there are any premixes or base mixes that are created that then later go on to have like different seasoning blends added to them and are destined to become different products, those premixes, you can vouch for those premixes as well as the final products. So one of the reasons that this analysis is so important is that it actually cooks these ingredients. So it cooks them, and in cooking them, it makes them perform the way they're supposed to perform. So in some sense, you're simulating processing conditions at lower solids, which amounts to a really big magnifying glass for looking at ingredient functionality. You're really looking at how these things do what they're supposed to do. And then as you're verifying the final mix performance, that's maybe the most important step, because things can go wrong right up until the final product is packaged. And if you're not screening the final product for optimal performance, then all of your careful work to optimize ingredients, the premixes, all that stuff, all that could be for nothing. All that, if you're the salmon and you have carefully swum upstream to the place of your birth, if you are incautious for just a moment, then it's still curtains. So there is some publicly available research for baked mixes that's based on this technology. So, and as we're talking about batter mixes and these stabilizer mixes, they're really not that different from each other. They both have a starchy component, they both have some components. So we evaluate their overall performance in much the same way. So one way that the academic community has decided to illustrate this with the RVA is to do it with bake mixes, because there was a long established set of best practices for test baking, muffins or cakes or cookies or things like that, and then they physically measure them with calipers or a texture analyzer or things like that. And what we heard from the test baking community was that they didn't really think that this was that descriptive at detecting changes in mix composition or individual ingredient performance. So they set out to prove that the RVA was better at identifying overdoses and underdoses of functional ingredients than these standard, make the finished food and then physically measure it sets of analysis that they were doing. And so what they found was that their suspicions were right. It does. It reliably detects over and underdoses and deviations from control. So here you can see a cake mix that they had that had overdosed and underdosed sugar, for example. But it's all variations on a theme. If a component is out of balance, it will have a characteristic deviation from control, depending on what it is. So you can see here that anything in red represented a statistically significant difference from control. There's a lot of red there. It picked up a lot of different ingredients, and then the physical analysis of finished cakes in this instance, not as much red. It wasn't even very good at detecting deviations, and it didn't detect over and underdoses of flour, for example. So it pays to have a bigger and better magnifying glass like the RVA when you're evaluating ingredient functionality. Not only is its throughput higher, but the descriptive power is way, way better, and it allows you to keep closer tabs on ingredient performance. So to what extent are mixes all the same, right? I just mentioned that they're not that different, whether it's a stabilizer blend or a bake mix or a batter or a breading mix, things like that. This application holds up for all of that stuff, this device and this application. You're finding the deviation from control. You're finding the weird thing that you want to get out of there. And it makes it pretty easy to identify a control or an optimal product. Let's talk to production and see how the product looks right now. And then in R&D, you can generate deliberate discrepancies that represent things that you would see out in the wild, out in production. And then you can tinker around with the little programmable robot chef to get the best possible combination of reproducibility and repeatability and descriptive power. And so this allows you to find the weird stuff every time, really reliably. If there's any deviation from normal in performance, you're gonna find it, and that's really all there is to it. So please do join us for the rest of this live meat and poultry webinar symposium. Our experts will be on hand to answer any questions that you may have. They'll have full contact information, and should be some really interesting stuff. So if anybody wants to reach out to me, I'm happy to take anybody's questions or provide more information about these applications. Just feel free to reach out to me at charles.kauffman@perkinelmer.com. And thanks everyone for your attention today, and we'll talk to you next time.